Hi, my name is Anisha Prathy, and today I'm going to be presenting with Sophia Hubsher, Rishik Janaswamy, and Ashley McNamara on the work that we did on sublinear time eigenvalue estimation for data science with Professor Cameron Musco. What if you were to try to unlock your phone using facial recognition, but it took way too long to unlock? Well, this might be because some facial recognition technologies use eigenvalues in their computations. Eigenvalue computations, when used on large datasets, can take up a lot of time and processing power. And so the research that we did helps to find ways to decrease the amount of time and power spent making these computations so that facial recognition technologies, such as the one that your phone uses, can work faster. Eigenvalues can provide information on the variance, dimensionality, vector direction, and more of a matrix that a large set of data might be stored in. They're used in fields such as artificial intelligence, social media, healthcare, communications networks, finance, and more. And so these algorithms not only make facial recognition technologies work faster, but they could also be applied to several other industries to make the technologies that they use much more efficient as well.
Before we get into our specific research question and the way that we went about addressing that, though, a quick recap on what an eigenvalue actually is. So if you take some sort of matrix A and apply a transformation to it, most of the vectors associated with that matrix are going to point in different directions after the transformation as opposed to before. Your eigenvector or eigenvectors, though, are going to point in that same direction before and after the transformation. The eigenvalues, which are the specific quantities we're trying to estimate in this project, are going to be the scalars that you multiply those vectors by so that that whole equation remains true. And this might feel really abstract, but it can actually tell us a lot about our original matrix, specifically with things like direction, dimensionality, clustering is a big one. For example, let's say we have a matrix that's all zeros with a cluster of ones here and a cluster of ones down here. We could try and visualize that by printing it all out. We could try and sort of read through the numbers, but what might be easier is to get that eigenvalue, see that there are two, one's bigger than the other, and that sort of gives you an idea of what your matrix looks like without you having to do a bunch of visualization or other sort of taxing computations there. So this is really useful information to have. It is unfortunately also kind of hard information to get, especially with a big matrix, just because it scales so poorly. So the runtime complexity for calculating an eigenvalue is somewhere around O of n to the 2.37. To visualize that, if you have a 1 by 1 matrix, that would take 1 unit of time to calculate. Now we only go up to a 10 by 10 matrix, suddenly that's going to be over 200 units of time. So now imagine you're working with millions by millions. It sort of just gets ridiculous. And then that leads us to our personal research question, which is, how can we estimate these eigenvalues in a way that maintains that accuracy enough to be useful and used in data science while minimizing the runtime? You just want to find out about the clustering. You don't want to wait 3 hours. So that's what we're trying to solve.
So previous theoretical results have shown that randomized sampling algorithms lead to accurate eigenvalue estimation, but this hasn't really been thoroughly tested on real-world datasets, and the accuracy and speed could be further increased when actually applying the algorithms to real-world data. So our primary algorithm that we implemented uses randomized sampling. I'll walk through a very small scale example to help explain how the algorithm works. So to start, a form of random sampling is used to choose n indices from the original matrix, with n being the sample size. For this example, n would be 2. We then select both the row and column at each of those randomly chosen indices, and create a new n by n sample matrix completely made up of the elements found at the intersection of those selected rows and columns. So in this case, that would be 2, 9, 9, and 5. And then we calculate the eigenvalues of this smaller matrix rather than the larger original matrix, which now leads to a much more efficient calculation. To go with this primary algorithm, we implemented two different random sampling algorithms, uniform sampling and sparsity sampling. To demonstrate how these different forms of sampling work, I'm going to use a graph, but for the actual algorithm, this graph would need to be translated into an adjacency matrix. So in these figures, for each point, the level of darkness of the gray corresponds to the probability of that point being sampled, with darker points meaning the point has a higher probability. In uniform sampling, each point is the exact same shade of gray, since every point, or index, has an equal probability of being sampled, which makes it uniform. In sparsity sampling, the points with lots of connections are darker gray, and the points without connections are very light gray, since in this method, points with more connections have a higher probability of being sampled. This algorithm is specifically effective on sparse matrices, and now a sparse matrix is a type of matrix that doesn't have a lot of data, meaning it has a lot of zeros, or represented in this figure as points without many connections. So sparsity sampling is effective since it does a better job of sampling the actual data out of the sparse matrices, since the points without many connections don't contribute as much to the eigenvalues.
Efficient computation of matrix properties, particularly eigenvalues, play a very pivotal role in data analysis. Through our research, we tested the sparsity sampling algorithm as well as the uniform sampling algorithm on large real-world matrix datasets. The following is an adjacency matrix which represents Facebook's social network graph. A red square symbolizes a connection between one user and another, whereas a white square symbolizes no connection between the users. Calculating the matrix properties, such as its eigenvalues, from the Facebook Snap matrix data yields insight into the social network's graph and attributes, including its connectivity, its centrality, and its clustering coefficients. And calculating these eigenvalues as fast as possible with a very high degree of accuracy is crucial for various reasons, including operational efficiency, real-time analysis, such as social media monitoring and online advertising, as well as expedited parameter estimation. Based on our results, the sparsity sampling algorithm outperforms the uniform sampling algorithm as it has an overall lower error percentage. This means the sparsity sampling algorithm led to more accurate estimation of the eigenvalue than the uniform sampling algorithm. Diving deeper into our results, when sampling 25% of the original matrix, the eigenvalue calculation speed increased by over 99% for both methods, with an average of 88.2% accuracy for the uniform sampling algorithm and a 98.6% accuracy for the sparsity sampling algorithm. The accuracy maintained within the sparsity sampling algorithm shows that these algorithms have the potential to be utilized in relevant fields to greatly increase computational efficiency. Many real-world systems and phenomena exhibit sparsity, and the prevalence of sparse matrices in the real-world applications can be attributed to the inherent sparsity of our underlying systems. For example, in social networks such as the Facebook Snap matrix graph, most of the individuals are not directly connected to each other, resulting in a sparse adjacency matrix. The sparsity algorithm outperforms the uniform algorithm because the sparsity sampling algorithm takes advantage of this characteristic by selectively sampling the non-zero entries, which contain the essential information about the graph structure and its relationships. Uniform sampling, on the other hand, would treat all entries equally, including the zero entries, resulting in a less efficient use of resources. Sparsely sampling allows for efficient data acquisition and storage. Since sparse matrices have a lower density of non-zero entries, fewer samples are needed to accurately represent the information of the matrix compared to a uniform sampling algorithm. And so understanding and effectively utilizing sparse matrices is crucial in various fields, including scientific computing, machine learning, and network analysis. Overall, sparsing sampling is more effective than uniform sampling on real-world datasets because it leverages the sparsity of the matrix, it reduces data requirements, and it improves the computational efficiency. These advantages make sparsity sampling a valuable approach for analyzing and processing large-scale real-world data.
In terms of our plans for future work, we would like to test on larger matrices and datasets and parallelize the algorithm further, seeing what changes and enhancements we can make to these algorithms to make them even more efficient than they already are. We would also like to thank Professor Cameron Musco in the Theory Lab, as well as Professor Nina Thoda and the ERSP program for this opportunity. Thank you for listening to our presentation.